I would like to thank the organizers for inviting me to be here today. It's a pleasure. So I'm going to talk about advances in African horse sickness vaccine research. And what I'm not going to do is overload you with technical data, but more explain the rationale behind all the efforts that researchers have been working on to develop new vaccines for African horse sickness. So African horse sickness needs very little introduction after the fantastic talks by previous speakers. So it is a highly lethal disease, and it has a high impact from the socioeconomic point of view, animal welfare point of view, and international trade. So what is it with international trade? International trade of horses is the motor of the equine industry. The equine industry is growing exponentially, but it depends on the movement across international borders of equine athletes. This is just to give an example of the magnitude of this movement of horses. These are all the trajectories or the destinations of a competition horse in a single year. And so, as I say, this is vital for the equine industry. And some countries have demanded a facilitation for movement of horses across international borders. And the OIE, together with the International Federation of Horse Racing Authorities and the Fédération Équestre Internationale, came with the concept of high health, high performance horse, which sets the basis or the provisions under which these high competition animals can be moved safely across international borders. And this concept of this scheme is based on OIE principles. And it has identified various equine infectious diseases that are very important to control. And African horse sickness, as previously mentioned by Suzanne, is one of the priorities. So the control of African horse sickness has acquired international dimension. It's more important than to become aware of this. So control of African horse sickness depends on a series of measures: early warning systems, rapid accurate diagnosis, the control of movement of horses, compartmentalization, zoning, vector control, vaccination, and efficient veterinary services that can implement efficiently and coordinate all these measures. But perhaps vaccination is the measure that it is suboptimal, or at least has a margin of improvement. So vaccination currently is done using attenuated live vaccines. These vaccines are based on repetitive virus passage in cell culture. They are administered as combinations of serotypes, as indicated there. Vial 1 contains serotypes 1, 3, and 4. Vial 2 contains serotypes 2, 6, 7, and 8. And the vaccination is applied from 6 months and then annually in endemic countries, and is normally efficacious. However, they present a series of drawbacks. They are produced mainly in Africa, mainly in South Africa, and if there's an outbreak in a non-endemic region, there will be a delay between the epidemic and the deployment of the vaccine. These vaccines are based on historical South African strains, and there is also the reversion the risk of reversion to virulence and transmission of these vaccines in the field. Also, there is risk of gene segment reassortment. So new strains with unpredictable biological characteristics can be generated if this happens. This is not recommended for pregnant mares, and they have no DIVA capacity. So studies by a former student of Professor Mertens showed that field isolates of an Ethiopian outbreak matched very closely to South African reference strains that were isolated 40 years ago, and also very similar to a Senegalese vaccine strain. So the only explanation for this is that somehow these vaccine strains have been circulating in the field, or there has been reassortment between vaccine strains and field strains. So inactivated vaccines are safer than attenuated, but yet biocontainment is necessary for manufacture at industrial scale. There's much less data on their efficacy, And the last time they were used, as Jose Manuel indicated, was during the Spanish outbreak. These vaccines are not available today, but there's a resurrected interest in exploring this type of vaccines today. And repeated inoculations are probably necessary to achieve a good immunity. And the DIVA capacity of these vaccines is very limited. Serologically is not possible. And by RT-PCR, in theory it is, but requires further investigation and generation of new data to support policy making. So classical vaccines and AHS freedom are largely incompatible. And this is because systematic vaccination confounds the interpretation of diagnostic tests that are used in surveillance, therefore making it very difficult to determine whether a country is African horse sickness free or not. So that is the case, and also previously mentioned by Suzanne, an AHS-free country is that country that, apart from other conditions, where the vaccination is prohibited. So this is a map of South Africa that adopted a regionalization policy to be able to export horses. So there's an African horse sickness-free zone in the metropolitan area of Cape Town, surrounded by a surveillance zone and a protection zone, and then an infected zone. Vaccination is practiced in the infected zone on a mandatory basis, and also in the protection zone on a mandatory basis, and also this vaccination is enforced. And vaccination is not practiced, it's prohibited in the surveillance zone and the African horse sickness-free zone. So our colleagues in South Africa worked tremendously to control African horse sickness in their country, but this system is very challenging, not only because African horse sickness is endemic in the country, but because classical live attenuated vaccines are used, which are very difficult to be used in surveillance programs. So the surveillance in the surveillance zone is done on serology basis on sentinel animals. And finding seronegative animals to be placed in this area is also not easy. If a DIVA vaccine was available, it would be possible to vaccinate horses in the free zone and in the surveillance zone and still be able to do surveillance activities. So therefore, you could protect all the horses and still be able to conduct surveillance and know whether African horse sickness virus has invaded the area or not. If we go to a non-endemic situation, if there's an outbreak, all the cases will be contained in a control zone in the center, as you can see there in the diagram, and there will be establishment of a protection zone, and surrounding the protection zone, a surveillance zone. If vaccination is applied, it will only be done in the protection zone. But there's a dilemma as well in non-endemic countries. The dilemma is if a neighboring country has African horse sickness, the dilemma is whether to vaccinate the population or not with a vaccine that does not allow differentiation of infection from vaccination and also has the capacity to transmit in the field. If a DIVA vaccine is available, all these problems are solved. You can apply vaccination to your population and still you can consider your country free of the disease. So the benefits of DIVA vaccines are DIVA vaccines could be applied to the general population without compromising disease-free status or surveillance. DIVA could be used in surveillance zones and free zones. The incidence and prevalence of AHS in the horse population could be monitored using DIVA tests during and after the outbreak. And all these will simplify containment measures and policies, facilitate eradication and the return to disease-free status after an outbreak, and in the end facilitate international trade. So I'm going to explain now different vaccination, different strategies that have been used by researchers to develop DIVA vaccines. This is a schematic of the African virus particle. It contains 3 layers of proteins, the outer layer formed by VP2 and VP5, which are the main targets of virus neutralizing antibodies, the middle layer formed by VP7, an immunodominant diagnostic antigen, and VP3, which is the inner core protein. The capsid encloses 10 segments of double-stranded RNA and the viral proteins involved in the replication of the virus. So a DIVA vaccine strategy has two components: a vaccine, which is a virus-like particle, or a viral protein, and the important thing is that it lacks a diagnostic antigen, and the second component is the differential diagnostic test, based on an antigen that is not present in the vaccine. I have tried to summarize the different DIVA vaccination approaches, and I have categorized them in three main categories. One is the genetically modified vaccines, and these are vaccines that are based on the whole virus particle, either attenuated or inactivated. The only difference with the live attenuated vaccines is that these vaccines have generated synthetically using reverse genetics. The technology offers tremendous possibilities, and Van der Water and colleagues in the laboratory of Piet van Rijn have done a fantastic job showing the potential of this approach. The advantages of this type of vaccines is that potentially they will induce very good immunity, as it contains most of the viral proteins of African horse sickness. The disadvantages are probably demonstrating biosafety, and also that DIVA might be a bit difficult to achieve with this type of vaccines. A second category of DIVA vaccine is which I called a subunit approach. And these subunit vaccines are based on the expression of African horse sickness antigens in vitro, mainly by baculovirus system. These proteins are then purified and used with an adjuvant to inoculate into the animals. And there are two subcategories in this, either using VP2-based vaccines, as described in the studies by Roy and Scanlon, for example, or using virus-like particles. These are proteins that are assembled in vitro to form a virus-like particle without the genomic DNA. The advantages of this type of vaccines is they are very safe, potentially very efficacious, and potentially would offer a very good duration of immunity. Disadvantage is the poor stability, and the yield is very low, so it is very difficult to scale up the production in an industrial setting. And the third type of vaccine, DIVA vaccine approach, is using viral vectors. And basically, here the immunogen is another virus, completely innocuous to the horse, which carries the gene that encodes for a protective antigen of African horse sickness. In this case, is the antigens that are expressed in these viral vector vaccines are either VP2 or VP2 and VP5. And these strategies are exemplified by the studies described in the slide. The advantages is that these vaccination approaches uses as a DIVA vaccine already developed tests, which is the VP7 diagnostic test, either serology or the RT-PCR test. The disadvantage is that it is furthermore work is necessary to prove that this vaccination strategy can work in a polyvalent fashion. So I'm just going to give an example of how these DIVA vaccines might work with a practical example using the viral vector approach. So as I mentioned, this type of vaccination strategy would be based on expression of VP2 and VP5 and using VP7 as a differential diagnostic test, either in a serology or as an RT-PCR test. And both tests are prescribed tests for international trade currently. So basically the gene of, that encodes for VP2, in this case, is inserted into the genome of modified Vaccinia Ankara virus. This is inoculated into a horse as a vaccine, and the horse, it is hoped that it will be protected. The animal will develop antibodies against VP2, but not against VP7, and it will not have viral RNA of African horse sickness virus. So this horse, it will be protected and also could be differentiated from an infected animal. So we conducted a study where 4 horses were vaccinated with this type of vaccine twice, and then challenged on day 35 with a virulent challenge with AHSV 9, together with 3 control horses. The animals were monitored, and the results are, as you can see here. The controls developed pyrexia, depression, palpebral edema, and there was a rapid progression of the disease, and all 3 controls succumbed to HS between days 5 and 6. There was no clinical signs and no pyrexia from the vaccinated animals, and post-mortem findings consisted of fibrinous gelatinous edema in the intermuscular fascia, subendocardial hemorrhages, hydropericardium, congestion in the liver, spleen, kidneys, and the stomach mucosa. Analysis by PCR and by virus isolation of blood samples are displayed in these 2 tables. As you can see, the vaccinated animals were completely viremia-free during the study period, in contrast to the control animals. Results by RT-PCR showed something, somehow were a bit different. So again, the controls showed viral RNA in their blood, but the vaccinates also showed viral RNA in the blood. This is using the diagnostic VP7-based RT-PCR assay. Results by serology showed that all vaccinates developed neutralizing antibodies, and then those antibodies rose further after challenge. And results by the DIVA test, by the VP7 ELISA, showed that by day 34, which was the day of the challenge, all the samples were negative in the vaccinated animals, and all these samples on day 62 after challenge were positive. So all these results, what do they tell us? So before challenge, MVA VP2 vaccinated horses developed an antibody response only against VP2. They were naturally RT-PCR negative, and the vaccinates at that stage could be differentiated from a natural infection. So after challenge, the animals were completely protected against African horse sickness disease and death, and the vaccinated horses developed a VP7 antibody response and RT-PCR positive. These animals were RT-PCR positive, also measured by the differential DIVA test. So these results indicate that these animals, despite being protected, we could determine that they were exposed to African horse sickness virus, at least to a challenge virus insult sufficient to generate a certain level degree of viremia that could be detected by the differential diagnostic tests, proving that this strategy could work as a DIVA protective vaccination strategy. So we have seen that these applications of research on African horse sickness have been highly successful in serology, as ELISA has replaced virus neutralization test and complement fixation test in most labs, and also RT-PCR methods have replaced virus isolation methods. But these applications have not been translated into the vaccinology field. And there are a number of factors that have contributed to this. I mean, to develop a vaccine against HS, you need a continuous large investment and vaccine industry support. So it is not possible to go beyond proof of concept if these 2 elements are not in place. And perhaps there has been, over the years, lack of communication between vaccine producers, governments, researchers, etc., and that resulted in too many different technologies. And I think the most important factor for DIVA vaccines not being in the market today is the market failure. African horse sickness equine vaccine market is not attractive for big vaccine manufacturers, and this is something that needs to be addressed. And just to last a couple of slides to finish, we are trying to address some of these difficulties in the context of a project that has been funded under the scheme of scientific activities to support the control of specific equine infectious diseases. and specifically against African horse sickness. And the objectives of this project are three. One is to develop an improved or to revalidate the VP7 ELISA and demonstrate that it could be a very good tool for improved surveillance. The second objective aims at estimating the equine population at risk of and to be protected against African horse sickness by a DIVA vaccine. So basically generating data that can be used to develop a business case with which one can convince vaccine manufacturers to invest into this type of vaccination strategies. And the third objective is to evaluate and prioritize the different DIVA vaccination strategies that are available against African horse sickness. And for this project, we have the pleasure to work alongside this number of laboratories and experts in different fields, from epidemiology, veterinary economics, diagnostics, vaccination, and molecular biology. And I would like to finish by saying that African horse sickness is a very little disease, continues to be a threat to animal welfare, and blocks the growth of the equine industry. Significant progress has been made in African horse sickness vaccinology, and there is a scope to improve vaccination strategies. And the first steps have been made to engage industry, international organizations, researchers. And it is absolutely critical that these initiatives continue, that the collaboration between different labs, different countries, and different agencies continues. And I would like to thank many people, as you are listed there, funders, especially DEFRA, who supported us in our vaccine work. And I would like to take any questions if there are any. Thank you.
Thank you, Javier. Thank you very much. Do you have any question for Javier? Oh, we are all experts. Yes, Peter.
Thank you, Stefan. It's really a question for Javier and the panel. I mean, I take on board Jose's specific comments that horses are not sheep, which is valuable. But horses, particularly, some of them are not only family members, some are very valuable. So because of that, does the panel think there's also scope perhaps for development of an immune therapy or an antiviral strategy that might be used for animals, perhaps post-recognized exposure to the virus, to save these animals that are really highly valuable?
Yeah, in the context of immunotherapy, I think it is very important that that possibility exists. We have done a few studies where we have shown that passive transfer of hyperimmune serum from vaccinated animals to immune recipients could protect, I mean, this is in experimental mice, could protect completely animals from succumbing to African horse sickness infection. And I think there's a value for this type of work, since individual thoroughbreds are worth lots of money, and if they become infected with AHS, is a question of probably the animal is going to die if there's no effective treatment. So I think there is a scope to develop just justification to develop this type of intervention, I think.
I can just complete that we are involved in a project on antiviral in equines, not on African horse sickness, although we can include African horse sickness, but on West Nile, for example. And yes, in certain situations, this could be of interest, I agree. Yes, Peter.
I just wanted to offer one other comment. I mean, particularly Javier's development of subunit vaccines and maybe Alan's work with canary pox as well. The big difference between these vaccines and the live attenuated vaccines, the attenuated vaccines are available now. So what would we do in the face of a sudden outbreak of disease in Europe if these other better vaccines are simply not available? would we be forced to use the attenuated vaccines? So I mean, Javier's point, we need to move this forward. We need to have these things available, I think is the next hurdle we have to jump.
Yeah.
I fully agree. That's why we have this day today, and I fully agree with you.